next talk is given by Pietro Andreani from Lund University, and the title of his presentation is Phase Noise in Oscillators. The bio is as follows. Pietro Andreani received the M.S.E.E. degree from the University of Pisa, Italy in 1988, and the Ph.D. degree from Lund University, Sweden in 1999. Between 2001 and 2007, he was chair professor at the Center for Physical Electronics, Technical University of Denmark. From 2005 to 2014, he had a 20% position at analog/RF designer at Ericsson AB in Lund, Sweden. Since 2007, he has been associate professor at the Department of Electrical and Information Technology, Lund University, working in analog mixed-mode RFIC design. He was also the head of the VINNOVA Center for System Design on Silicon, hosted by EIT 2014 to 2016. He has been a TPC member of ISSCC from 2007 to 2012, is a TPC member of ESSCIRC, chair of the Frequency Generation Subcommittee since 2012, TPC chair in 2014, an RFIC, and an Associate Editor of JSSC. He was an IEEE Circuit Society Distinguished Lecturer in 2017-2018. He has authored numerous papers on oscillators and phase noise. And believe me, if you want to listen about, learn something about phase noise and oscillators, he's the right person. So thank you.
Thank you. I apologize for the overlong CV. I didn't realize it was going to be read aloud. And I hope you had a light lunch, because although phase noise mixes basically with everything, it does not really mix very well with food. So, and this is the overview of my talk. And you can see here it's about popular harmonic oscillators, and then something about phase noise, and architecture for low 1/f² and f³ phase noise. A few slides about the new, more fancy concept, the series resonance oscillator, and final design techniques for a very wide frequency tuning range, RF CMOS VCOs. So, almost invariably, the oscillator, the harmonic oscillator is set up around so-called LC tank because it acts as a reservoir of energy, and the inductance and the capacitance that make the tank are connected almost always in a parallel fashion, and in this case the resonance frequency is exactly equal to 1/√of LC, the angular, of course, omega 0. Now, in reality, obviously, these components have losses, in this case, series losses, but if these losses are not very large, then the resonance frequency is still very close to the previous one. Typically, we want to compact all these losses in an equivalent parallel tank resistance, as you can see here, with a big R in parallel to L and C. And this is because then at resonance, the impedance of the tank is immediately given by exactly this resistance R. Now, obviously this resistance tends to kill any oscillation that would be in the tank, and in order to compensate for that, we need an active negative resistance in parallel to that, minus R active, as you can see here. Notice that since it is in parallel, in order to make an unstable system, which is what an oscillator is, we need an R active that in absolute value is lower than R. So, and if it is lower, then it really means that we have to burn more power. We would like this to be really high. And finally, we also, for convenience, define the quality factor of this LC tank as the ratio of the impedance of the capacitance or the inductance at resonance. They are basically the same. Sorry, that could go to the denominator, and to the numerator there is resistance, parallel resistance of the tank. So in this case, as you can see, ideally this resistance is infinite. Okay. So how do we implement now this minus R active? There are a number of ways, and one which is very popular, has been at least very popular, and for reasons that I do not totally fathom, is still quite popular in the millimeter wave field, is the Colpitts, so-called Colpitts oscillator. So this was invented by an engineer named Colpitts around 100 years ago, and very beautiful construction. Is basically needs only one active components if we, for the time being, disregard the way we implement the current, the ideal current source at between source and ground. The negative resistance in this case is implemented via positive feedback around the device. In this case, a MOS device. It could be any transistor, though. So this feedback is given from the path from drain to source across the two capacitors, as you can see here. The way the oscillator works at steady state is very non-linear, as you can see here. Typically, the current is supplied to the tank with brief and tall current pulses. So they are very harmonic rich. If they are, if the tank has a quality factor which is at least reasonably high, all the higher harmonics beyond the fundamental will be filtered off by the tank itself. So the waveform that we collect at the drain of the transistor is very close to purely sinusoidal. And also notice that this oscillation, this voltage oscillation, swings above and below VDD in this implementation. By the way, it could appear to be, an analysis, a more in-depth analysis of this oscillator. For instance, one telling us what the amplitude of oscillation is given the values of the passive components and the current may appear very difficult, but in fact it's not. It's not. If we resort to the approach so-called of the describing function, and what I've said, talking about in the previous slide, was that all the higher harmonics of the current are filtered off by the tank. So we assume that they do not really make any impact, and so we substitute the transistor with the value of the fundamental current harmonic, as you can see here. And of course, this fundamental current harmonic, its amplitude is dependent on the oscillation amplitude. So obviously, we have some issue here, but we can make a first-order approximation, which turns out actually to be pretty good anyway. Basically, that these current pulses are almost like Dirac's deltas. And if this is the case, then we know that just by Fourier transform, we know that then the amplitude of the first harmonic of the oscillation is ideally equal to 2 times the DC value of the bias current. And so if we adopt this first order approximation, which I repeat nevertheless is very good, we end up with these equations. Obviously we retrieve, well not obviously, but we do retrieve even for large signals the oscillation amplitude, the oscillation frequency that we already saw for the plain tank. And then we have the oscillation amplitude which is again given by this value, basically the value of the harmonics of the current at omega 0, the impedance of the tank at omega 0, which is by definition R, the parallel resistance R, and then we have a factor of 1 minus n, which actually we would like not to have there. It's basically n is the feedback factor that actually enables the negative feedback, the positive feedback, and as you see here, given in the equation here. N is lower than 1, but is not negligible, so the factor 1 minus n is definitely lower than 1, and this really it means that our way of implementing the negative resistance has an impact, a deleterious impact, on the maximum amplitude of the oscillation that we can obtain. Now all this is really beautiful, but nowadays, at least at lower gigahertz, say below 10 gigahertz for integrated oscillators, we do need anyway two opposite phases, not only one as was in this case. So the real star of the implemented VCOs is oscillator is this one. It's unfortunately it really lacks a nice name like Colpitts, Hartley, Clapp. It's referred to in different ways like cross-coupled differential-pair oscillator, something like that. And this is definitely the most popular integrated oscillation family. And you can see here what the current does in this case. So while I forgot to mention in the previous slide that the Colpitts oscillator works in so-called class C, meaning that the transistor carries all the current over a time which is less than 1/2 of the oscillation period. In this case, basically the oscillator works in class B, meaning that each transistor carries all the bias current for approximately half of the oscillation period. And you can see also in what way there is a so-called center tap in the middle of the inductor, and so for half of the time the current flows all the way, say, on the right side, and for half on the left side. So the current waveform is a square waveform. Again, harmonics rich, but the higher harmonics are filtered by the tank, which means then that the oscillation, the voltage is very close to purely sinusoidal. In this case, very symmetrical in phase opposition, and once again swinging above and below VDD. The fact that so if we calculate this at the resonance frequency, now we know that the value of the current, the fundamental current harmonic for a square wave oscillating between IB and 0 is 2/π times IB, and then this is multiplied by the impedance of the tank. Actually, it's pretty easy to show that it's just half of that. Basically, since we inject the train of current through the center tap, it really means that each current waveform only sees half of the tank impedance at resonance, which is R/2. Differentially, we have an oscillation amplitude of 2/π times IB times R. Equally, almost, I guess, well, equally famous, I guess. It's the same oscillator, class B oscillator, but in this case with a double switch pair. It's basically a case of current VUs. Okay? So if we have enough VDD, we can use the same current to let it flow through a differential pair, so a cross-coupled differential pair implementing in a very straightforward way the negative resistance. But in this case, it flows also across the differential P MOS pair. So roughly speaking, we get twice as much negative transconductance or half negative resistance for the same current. Okay. And because of this, it is extremely popular. Notice though that in this case, single-handedly, the oscillations are not purely sinusoidal, okay? Because when, in this case, the one PMOS transistor is on, then the respective output gets connected, stuck to VDD. And it's only when this transistor goes to off, and then the oscillation is released. So you can see it basically in this case, as you can see here. In this case, it's easier to look at the differential waveform of the current, which across the differential tank oscillates between IB and minus IB. And this means that the oscillation amplitude is 4 over pi times IB times R. So actually, the oscillation amplitude compared to the previous oscillation architecture is twice as large if the tank is the same and the bias current is the same. So it's twice as efficient in terms of current utilization. On the other hand, as you can see here, the oscillation voltage cannot climb above VDD. The oscillation voltage is stuck between ground and VDD, while in the previous case, it could actually, ideally, swing all the way from ground to twice VDD. So it's better for the usage of the current, but in the same way, less efficient in the use of the voltage. And this will be used later on. Now, something about phase noise. You have already heard a lot about phase noise, and I don't know how much I should go through here, but you can see here that, as we have already seen, the phase uncertainty of a free-running oscillator, so an oscillator that is not inside a feedback loop like in a PLL, grows unbounded in time. So after one, we would not have any idea when the zero crossing would occur. This is, so it's in the time domain, as we have seen, is referred to as jitter. But if we focus more on, say, wireless applications, then there is more information actually in the phase noise, as you can see here, which really gives us you can see in this case, is calculated, as we have already seen, calculated as in dB with respect to the carrier here. So this difference, and is calculated in a bandwidth of 1 hertz. Okay, so we are actually interested in knowing not just the total power of the jitter, but actually when the spectrum of the oscillation, how much noise it carries at different so-called offset frequencies from the ideal omega 0 carrier. Why then should we bother about this? Well, there are at least, as you can see, there are at least 3 cases. So in a receiver, okay, it can down-convert large nearby signals on top of the desired signal. Okay, so talking about wireless radios. In a transmitter, it can increase the noise floor in the receive band, and in both it can corrupt the phase information in the signal. And so not seldom the phase noise performance of the oscillator, receive or transmit oscillator, is really the bottleneck for the whole radio receiver. Now, what do we do to, let's say that we want to calculate phase noise, okay? And what do we do? Oh, yes, sorry, I should have mentioned this. I'm not going through all the slides that you have in your proceedings, but I thought that it was better for you to anyway have also the slides that I skipped that make it a little bit more complete. So in this, let's go back then to the question here. How do we go about to calculate the phase noise? We can, of course, always try to start with the simplest approach, which is a linear time invariant approach, basically the one that you would use to analyze a low noise amplifier, basically where signals are very small compared to the bias point of the circuit. So we can do something like this, and then we can, as you can see here, we can add a further simplification. Let's say that magically we have managed to implement an R active minus R active, which perfectly cancel perfectly cancels the impedance, the parallel resistance of the tank R. So we are just left with L and C, and we want now to look at what is the impedance of this parallel combination, not at omega 0, because that we know that there it's infinite, but at an offset frequency delta omega. And so you can see it then here. So we can also rephrase this in terms of the quality factor of the tank, and we got this nice expression in terms of absolute value, which is repeated here. Now, what do we do with this impedance? Well, we can let the noise power density of the resistance, in this case refer to the current, so the current noise density, we can then let it act on this impedance and to basically generate a voltage noise across the tank. And you can see given in this way. Okay. Now, of course, this really accounts for all the noise generated by the resistance, but in fact, we are interested only in half of this noise, because if we assume that half, let's say that the noise does not have any preference whether impacting the phase of the oscillation or the amplitude of the oscillation. Now, if it impacts the phase, well, then we have to take that into account. If it impacts the amplitude, say to the first order, we can see that this is actually eliminated by the oscillator itself. Basically, if you have a steady state oscillator, if you disturb the amplitude of the oscillator with some noise impulse or so, after a few or many oscillation cycles, dependently on the quality factor of the tank, the oscillator will recover the nominal amplitude. So half of the noise is actually rejected by the oscillator itself, so that the actual phase noise is just half of this expression that you see above, and then divided by the power of the carrier. We assume here that we have a simple sinusoidal carrier, and so this is an expression of the noise, which obviously is absolutely the minimum possible phase noise that you can measure in an oscillator, because you have seen that we have disregarded any other possible sources of noise. For instance, the noise coming from the active resistance that we have disregarded. So this equation here is the fundamental part of a very famous equation, so-called Leeson's equation, a kind of heuristic phenomenological equation that was proposed in 1966 by Leeson, which has actually three different segments. So the first one, and you see here we have a noise factor F, accounts for the fact that we do not really have just the tank resistance, but also other resistances. Definitely, we are going to have the noise from the negative active resistance. Notice that this noise, the generation of this, say the noise generating this plot here, this curve is white, but because of this integration, and basically because of the fact that this delta omega, the offset frequency at which we calculate phase noise, it appears at the denominator. This phase noise actually grows as 1 over f delta omega squared, with delta omega decreasing. Next, we have, and this is actually becoming more and more relevant in CMOS applications, in nanometer CMOS processes, because then this is a phase noise that grows with the cube of delta omega. I should say 1 over delta omega. And this is because various sources of 1 over f noise in the oscillator, in the, say, the active components in the oscillator, this 1 over f noise can be so-called upconverted into 1 over f cube phase noise. And this is taken care of by this part here, where we refer to this parameter here as the corner frequency for upconverted 1 over f noise. Finally, we have, if you look at the spectrum analyzer, you can see a flat part of the spectrum. This is actually not intrinsic of the oscillation inner workings. It's in fact just due to the fact that after the oscillator you will have to buffer or distribute these signals to other parts of your design, or at least to the measurement setup, and all these blocks will have their own flat white noise. And so when the phase noise of the oscillator falls below this noise floor, then this is what you're going to see, but it's not really coming from the oscillator itself. Now all this is very nice, but it's not really enough to really assess or analyze the noise and the phase noise of an oscillator correctly. And this is basically because oscillators, we have already seen that in the two cases that we have presented, is really contains large signals. So there is not a bias point which is more or less fixed, but the currents and voltages across the oscillator vary very much, wildly across one oscillation period. So it was realized by some 20 years ago by Hajimiri and Lee, then at Stanford, that you really need a still linear but a time variant approach to the analysis of phase noise. And the paper that you see quoted here is still, I believe, the most cited of the Journal of Solid-State Circuits. It is easy to see why you need a linear time variant, so across the oscillation period analysis. So think of having just a simple LC tank like this, and then you inject some noise spike, some noise pulse across the sometimes during the oscillation period. So it really depends how much phase noise you get. Really depends on when you inject it. So for instance, if you inject it in this case, basically at the top of an oscillation, you see that you do not really change the phase of the oscillation at all. The phase is still the same. So in this case, there's basically no phase noise. Okay, it is a simplification, of course, but nevertheless. On the other hand, if you displace in time the impulse by 1/4 of the oscillation period, now you inject it at the zero, so-called zero crossing. And now you really have the dual situation. You don't disturb the amplitude, but you disturb the phase maximally. And this very simple example makes it, I believe, very clear why we need to take into account this thing in order to be able to really assess the way noise is converted into phase noise. Okay. By the way, I should also point out that, yeah, okay, we have disturbed the amplitude here, but I have already said that in a real oscillator, basically an oscillator which has a Q which is not infinite as this tank, then this disturbance dies out. So what we need is some equations in this case. So the bottom line is that every current source, noise current source, must be weighted by an associate function, the so-called impulse sensitivity function, ISF, also referred to as gamma by Hajimiri and Lee. And this gives you an effective current that then you use to calculate the phase noise. The gamma function is a Fourier series with period equal to the oscillation period. And once you have this effective noise, then the phase noise in the white noise region is simply given by this expression. So we need to take the square of the root mean square value of this effective noise and then divide it by the denominator that you can see here. An analog equation is valid for the upconversion of 1/f noise into phase noise, but we skip that. So, for instance, in LC oscillators, we see that very conveniently the gamma function is actually sinusoid, and it's let's say in most oscillators, I should point out. So basically all single-ended and differential oscillators, unless you do something to avoid that, but then the gamma function is in quadrature with the oscillation voltage. And this really gives us the possibility of doing calculations. I should also point out that this is a simplification. So again, we forget about the higher harmonics, higher order harmonics. We just keep omega 0 here, okay? But it turns out that in almost all cases is actually enough, especially if the quality factor of the tank is not ridiculously low. So we go back to our case, our LC tank, with the noise from the parallel tank resistance, and we see that what we get is this equation here. So we start from the equation from the previous slide, and now in this case, since this noise source is stationary, we can break down this into the stationary part of the current and then the square of the root mean square factor of the gamma function. The gamma function is a sinusoid, so all this is just 1/2. So basically, we recover Leeson with a noise factor of 1 in this case, because we haven't considered anything from the active part. But the nice thing now is that we don't have to say anything about that half of the noise goes into amplitude, half goes in phase. Then magically the amplitude noise disappears, and then we have just 1/2 in the final equation. In this case, it is the theory itself that takes care of this, so it's much more pleasing, of course, and obviously it shows that we are in the right track. Of course, now we can also proceed with the active part. Okay, the active part, and as usual, we assume that the noise is proportional to the transconductance of the transistor. So 4 kb Boltzmann, T, absolute temperature, gamma, channel noise factor typically equal, ideally equal to 2/3, and then GM. Okay, GM, for instance, in this case for transistor N1. Notice though that in this case GM is not a number. It is again a Fourier series in general, because the GM changes wildly across the oscillation period. For instance, when for half of the oscillation period, this transistor is off, and so obviously then GM is 0. So we can see that what really matters for us is when does this transistor and its counterpart generate noise? Well, it's when we have current commutation. Because outside of current commutation, meaning the current goes from all the way in N2 and then all the way to N1, basically over this very narrow segment of the oscillation period. Outside of this, we have either the transistor is off, obviously it doesn't generate any noise, or is totally on, but the other one is off, and then its noise is totally cancelled by the cascading effect given by the ideal current source at the source of the differential pair. So it's just across then this segment here, and we multiply then this GM, this current noise, with the associated gamma function. In this case, actually, the gamma function is pretty close to 1. So you could still pull it off without thinking in terms of, time variancy across the oscillation period, because multiplying something by 1 is really, like ignoring the multiplication factor. Skipping all the details, and of course, if you want to look at the original papers, they're all cited in the slides, and then there will be 4 slides in the end where you have all the the references. These are the results. Okay, so you see that in this case the noise factor is 1 plus gamma n, where again gamma n is the noise factor, the channel noise factor of the N transistor. Okay. So if the tank contributes for a factor of normalized to 1, then the contribution of the transistor, both transistors together, is gamma n. And the transistors appear only through this. So this is actually a remarkable result, because at least when I started working in this field, too many years ago, unfortunately, but nevertheless, it was still thought that, okay, so if I double the GM of the transistors, then I have a stronger oscillator and a more robust startup, but then I also double the noise of the transistors. But as you can see, in this case, this is not true, because the GM does not appear there. It's really remarkable. So it's always in the same proportion. And if gamma n is the ideal value, 2/3, then 60% of the noise comes from the tank and 40% from the transistors. I guess it's easier to assume that the gamma n is equal to 1, and then basically half of the noise is contributed by the tank and half from the differential pair. Now, how is this possible? So we can try to interpret the equations and see really what happens in the equations. So what happens is that, for the first thing, the transistor noise is proportional to the commutation time. Okay? The longer the commutation time, the more time has the transistor to generate noise that is injected into the tank. On the other hand, the commutation time is inversely proportional to the oscillation amplitude. The larger the oscillation amplitude, the stronger you drive the differential pair, the shorter is the commutation. And the oscillation amplitude, on the other hand, is proportional to the parallel resistance of the tank. So for the same current, if you double the resistance, the output resistance, then you have also double the oscillation amplitude. And this is basically why the two things are always connected. And notice that a simple-minded LTI analysis would really lead us astray, because we would, to repeat, assume that the phase noise really increases with the GM of the transistors. Another way of seeing this is with this plot from Maple. So the current noise, and here is basically the commutation time, or phase if you want. And as you can see here, if you double the gain factor of the transistor, obviously you increase the peak noise generated by the transistor, but you also shorten the commutation time. And the bottom line is that the two areas are identical. I would like to stress that this is actually to the first order, because now, of course, if we go and you know, we have a like really big transistor, to the first order, yes, this is still true, but having a really large transistor also increases the amount of parasitics, especially nonlinear parasitic capacitances, which are never really good. So we should try to limit the strength of the transistor to what is really necessary to cover all PVT variations, and not more than that. And if we do that, then basically this is true. Now, we said that by luck we could have derived this equation without thinking of the an LTV, linear time variant theory. And in fact, people came actually quite close to the equations that you saw in the previous slide. What would not be possible is to correctly assess the noise, phase noise in the Colpitts oscillator. Because in this case, what happens is that there is a huge difference between the noise and the effective noise. Remember, the noise is the noise generated by the transistor, but the effective noise is actually the amount of noise that really contributes to the generation of phase noise. And why is this? Well, because in this case, the associated gamma function is not at the maximum as in the previous case. It's not 1, but is actually 0 or almost 0. So you can see the difference between the blue curve, the noise that you would put in your equations if you didn't think of time variancy, and the red curve, which is the correct one. Again, doing the calculations, this is what you get. And once again, you can see that there is no impact of GM. So also in this case, as long as the transistor makes the oscillator go, its noise is not dependent on the GM, but only on gamma n, and also, of course, on the architecture of that we have selected. So in this case, we have selected the Colpitts, so we have this extra factor 1 minus n divided by n, and this also gives us the possibility of calculating the value of n, which gives us the optimal and optimal value for minimizing the phase noise, and you can see it here. Okay. By the way, if you look at this equation here and you put in the numbers, and you look also at the ideal equation for the differential pair oscillator, it turns out actually that the ideal differential pair oscillator is actually a couple of dB better in terms of phase noise for the same tank and the same power consumption compared to the Colpitts oscillator. By the way, so again, also in this case, no GM. So we have already seen that a couple of times, and in fact, this is a more general result. So we can actually show that if this impulse sensitivity function, gamma function, is sinusoidal and in quadrature with the tank voltage, the active devices work as transistors. So basically they are off, or they're in the so-called active or saturation region, but not, say, in the linear region, thinking of MOS devices. And also, the transistor current noise is proportional to the transconductance of the transistor. Then we can actually show that the transistor effective noise depends only on the tank loss and the actual topology that we have chosen, but not on anything else. And especially, it doesn't really matter what kind of transistor we use, of course, to the first order. All right. By the way, at this point, maybe I can have this slightly. I didn't know really where to put this slide. So here, I guess, it's as good as anywhere else. Some remarks about the symmetry, or actually the lack of symmetry between inductive losses and capacitive losses. So we have seen in one of the very first slides that the inductive losses are we could compact capacitive losses and inductive losses into the same parallel resistance, and we didn't really differentiate between the two. This is very often true. Almost in almost all cases, it is true. But in general, it is not. So if we have this value here, Gm at, say, the bias state, times Rc, the resistance series loss of the capacitance, if this is large, then the resistive losses of the capacitance actually generate much more noise, or even much more noise than the inductive losses. And another thing is that anyway, the GM, so the noise from the active part of the transistor, of the oscillator, is still anyway proportional to the total noise from the passive part. So if the noise phase noise increases because of this effect from RC, it also increases from the active part of the noise. And if you want to look at the details, please refer to this paper here. Obviously, this effect is totally lost if you start by compacting everything into an equivalent parallel resistance. We have, by the way, taken also our shot to a phase noise, more complete phase noise analysis, starting very simply with a very general transconductor GM and a very general resonator Y, of admittance Y. And the start is actually also very simple. Basically, what we need to know is that I is equal to Y times V, that's Kirchhoff, and then just that the fact that the transconductance is given by the derivative of the current divided by the derivative of the voltage. Okay. The different thing is that here we do not just stop at omega 0. We actually go beyond that and look at several harmonics. And this work was prompted originally because we wanted to understand what happens if we have a tank that resonates not only at omega 0, but maybe also at 3 times omega 0. The results are very rigorous for a very broad hypothesis. So you can see them here. We do not really need to go into the details. But the nice thing is that we can produce closed form and very very precise equations for the phase noise in the case where there are multiple resonances in the resonator. For instance, say that there is a resonation at omega 0 and 3 omega 0. Is it good to have, so let's say that you have a tank that resonates at omega 0, and you ask yourself, is it good to introduce a second resonance at 3 times omega 0? Does it make for a better, lower phase noise? You see the equation here, okay? And the equation compared to, you can imagine what happens if you have only one resonance. So basically that means that the oscillation amplitude at A3 at 3 omega 0, that would be 0. In that case, then you recover the standard equation for the simple LC tank. Now in this case, you see that the A3, so the amplitude at the third resonance, is present both at the numerator and the denominator. So obviously, that the denominator is good because it decreases the amplitude of this value, but it's also present at the numerator because now we have a resonance at the 3 omega 0, and then that noise can be transferred, folded back onto the carrier around omega 0 and add to some more phase noise. And it turns out that to make this advantageous, so that we actually end up with a lower phase noise, then the problem is that we need a quality factor at the third harmonic, which is larger and even much larger if you look at this plot here than the quality factor at the fundamental frequency. And this is not really easy to do in practice. I would like also though to mention that this technique is used a lot by, for instance, Professor Masoud Babaya at Delft. So maybe he would tell you something else. On a side, since I have put this slide back, since Professor Sheikh al-Islami was talking about the phase noise in ring oscillators, so this talk is about the harmonic oscillator, but since he was telling about ring oscillators, then I would like to mention that we have produced a phase noise equation for ring oscillators that improves, let's say, the state of the art in the equations for the phase noise in ring oscillators. Okay, fitting very well the simulations. Okay, let's go on. So let's go back to our nice oscillators, harmonic oscillators. We have seen that there were these differential pair oscillators, one with a simple differential pair, cross-coupled differential pair, and one with the stacked one. So the question is now, and also we remember that if we have enough VDD and everything is exactly the same, we have that for the oscillator on the left with a simple differential pair, then the oscillation amplitude is half of the oscillation amplitude of, sorry, was mirrored. So for on the right is the half of the oscillation amplitude than on the left. So my question is, of course, what phase noise difference should we expect from the two cases, right? Because a factor of 2 in amplitude is very simply 6 dB, okay, 6 dB. But what about the noise, or let's say the phase noise? Okay. One thing, obviously, which is obvious, is that here there are 2 transistors that generate noise, and on the other case there are 4 transistors. So also in this case, once upon a time, the reasoning went like this, that okay, so there are 4 transistors, but the noise is not correlated. So 4 is like 3 dB, and so 6 dB minus 3 dB, okay, maybe 3 dB of in favor of this oscillator. Okay. Now, if we again do all the calculations, we find out that these are the equations. Okay. And if you can look at, if you assume that gamma n and gamma p are where gamma p, of course, is the channel noise factor for p transistors, if they are the same, the only difference here is the amplitude. Okay, which is double in the double switch pair compared to the single switch pair. So the difference in phase noise is exactly 6 dB. It's like it's only the amplitude that makes a difference, and not the fact that there are 4 or 2 transistors. And this is basically, again, because the fact that if having a large amplitude is not good for the amplitude itself, obviously, but also for the generation of noise. Having a double amplitude, we drive these transistors more strongly, twice as strongly, let's say. So they have half as much time to generate noise. So they are 4, but they generate noise over half as much time. And so, again, the 2 areas are the same. And that's why. Amplitude is twice, but the phase noise, generating noise, is half. Right. Again, so this was a simple comparison between 2 oscillators, but what about if we have more oscillators? Well, people have come up with so-called, well, and now there are figures of merit for all blocks, all circuits, but especially in 2 fields that are really very important: oscillators and converters, A to D converters. In this case, for oscillators, you see what you have is that you have your phase noise, and then you normalize it to how much power you have consumed, what the oscillation frequency is, and also at what offset frequency, delta omega, you're looking at. Okay? So eventually, all this boils down to something like this. It's the square of the quality factor of the tank, KB over T. There's not much we can do about it unless we go like cryogenic or so. And then we have like efficiency of the oscillator and also the noise factor of the oscillator. And of course, these are important, of course, but in well-designed oscillators, they do not change a lot. So you can see from here really the impact of the Q. If you really want to make a great oscillator, you cannot really start with a bad technology where the Q is low. And you really want to have a Q above 10 and possibly around 20. Then you can really make a good oscillator. Or let's say, I should say, an oscillator with a really good figure of merit, which is actually not the same. It's not nearly as important if you come from from the industry. In academia, it's very fundamental. And for instance, in this case, you can see that we pick this again, the comparison between the single switch pair and double switch pair, and we can actually see that they are capable of exactly the same maximum figure of merit, but they are actually reached for vastly different power consumption regimes. Okay? So it's very, very interesting. And but Antonio Riscidini, who is going to talk after me, will talk more about this. So I will leave this for him to continue. I haven't said much about the biasing so far, and indeed, still it is really very, very, very important. Okay, biasing actually is not a second order issue. It's really a first order issue. So you have to be very careful with that. Typically, you have a couple of, well, you have more, but let's say that you have a couple of options very often. You can have a variable resistor, So the nice thing is that the biasing circuitry is really easy, very simple. There is no 1/f noise generation in these resistors, but the problem is that they have a low impedance. So what we have seen so far, remember that we assume that we had an ideal current source. An ideal current source has an infinity output impedance. But the resistances here are like, if it is 100 ohm, it's already a lot, okay? Unless you want to waste a lot of voltage dropping across this resistance. So they're small, and this impedance here is not very large. And the problem then is that there is then a significant conversion, especially of 1/f noise from the cross-coupled pair into phase noise, which can be really troublesome, Or you can go the other way around. So an active current source with a transistor, and obviously this is a high impedance source. That's great. So there's less subconversion of 1/f noise from the cross-coupled pair. Okay, but it does generate its own 1/f noise, and which can be actually very substantial. Another issue that is in conjunction to this is very important is the fact that so you see that there are like two sources and one drain at this node, at the common node there. So there's a lot of parasitic capacitance, Why are we concerned with that? Well, because a lot of parasitic capacitance and cross-coupled MOS entering the linear region, which is usually the case when you operate these kind of oscillators in the standard manner. So the two things together, devices entering the linear region and lots of parasitic capacitance there, then there is really a boost of both wide and especially 1/f noise into phase noise. Very troublesome. On the other hand, this parasitic capacitance is really good to filter off high frequency noise from the tail. And this brings me now to this part about architectures for low phase noise, 1/f cube and square and cube. And one thing, perhaps we can say the most successful technique to combat the impact of these parasitics is the one that you see here, the so-called noise filter. By the way, one of the author of this work, Henrik Sjöland, is my colleague in my department. You see that in this case, what we want to do is really to resonate, so to keep high impedance at the common source at the oscillation frequency. So you see that in this case we want L tail and we want that this parasitic capacitance C tail par resonating with an extra inductance L tail at 2i omega 0, which is the natural frequency of the common source. In this way, they boost the impedance at this frequency. It turns out this to be really, it's a really effective technique. Notice that in order to make them resonate, these lead of L tail must see a signal ground, so we short it to ground with a big capacitance. The nice thing about this big capacitance is that it also filters off even more efficiently the high frequency noise from the transistor, from the tail transistor. And also, since we need a big capacitance there anyway, it can contain, it can include the parasitic capacitances of these devices. So this is what I said. So basically, since these parasitics can be included in the C big, this transistor can be made wide and long. So long, why do we want to make this long? Well, because its 1/f noise falls with the square of the channel length. So it's very important to have it long. And then we make it wide so that it doesn't consume a lot of overhead. And this is the original paper from like almost 20 years ago, and basically it's figure of merit is still state of the art, although of course the oscillation frequency is low, and as far as I understand there's really no tuning range, so it's just one frequency, which makes it kind of useless to be used in practice, but nevertheless it's outstanding performance by them. You can see here that there is a big extra inductance, so you know the real state takes a hit a bit, but nevertheless this is so efficient, it's so effective that this technique is very often used. And you can see here a novel implementation, I mean a more recent implementation by the University of Pavia. In this case, oh man. In this case, they resonate not just this tail, but also this one. So they use actually a transformer instead of an L tail. They use a transformer, and they use a double switch pair topology instead of a single switch pair. This other topology here is just there to make a comparison. And if you look at the performance, it's really good. This is really state of the art. It's a very low phase noise, and for a very high figure of merit. And this combination, low phase noise, very low phase noise, and really high figure of merit, is really difficult to obtain. It's relatively easy to have a great figure of merit, but a not so great phase noise. But in this case, instead, is much more difficult. There are also alternatives, actually, to this explicit so this additional L tail, or in that case, a transformer for resonating the parasitics at twice omega 0. You can actually design the tank itself in a more complex way, again, as you can see, making use of transformers, so that the tank resonates differentially at omega 0 and single-handedly at 2 times omega 0. And this, the nice thing here is that this was basically presented back-to-back at the ISSCC a few years back by 2 different groups. So starting with Shah Mohammadi from Delft, you see that it's a so-called class F2, actually class F2 and F3 here, oscillator. And you can see here that there are not 1, not 2, but actually 3 resonances. So at omega 0 and 3 omega 0 is differential resonance, and at 2 omega 0 is a common mode resonance. And then you can see that at maximum and minimum frequency across the tuning range. And also in this case, they obtain really good performances, a good tuning range, a low figure of, a very good figure of merit, a low phase noise. The other group was by David Murphy and co-authors at Broadcom in California, and they did it actually with a single switch pair, and as you can see here, with a double switch pair implementation. In this case, they actually dispose altogether of any bias, so they are kind of constrained to have a precise VDD. But also in this case, it's a really good figure of merit. Actually, it's a great figure of merit. But again, it would be nice if they could try to obtain the same figure of merit, or approximately the same figure of merit, but at a lower, several dB lower phase noise. Anyway, these very popular techniques, they have really picked up a lot of momentum. Totally different approach is, well, the other way around, it's a class C. So basically not allowing these transistors to enter the linear region. Okay? And actually using C tail here on purpose. Okay, so if we keep N1 and N2 either off or in the active region, what we have here is basically a kind of ideal differential Colpitts oscillator. It's a kind of ideal differential Colpitts oscillator. So you see that the waveform of the current is the class C, so narrow and tall current pulses, and so the current efficiency is much higher. So it's actually compared to the class B oscillator, you ideally you get almost 4 dB lower phase noise for the same current. Also in this case, the C tail is very good for filtering off high frequency noise, and also it can be made long and wide. Okay, and here is the original implementation, which is after more than 10 years is still pretty good, with a very high figure of merit and the phase noise, which was actually still quite competitive. There are, though, some issues, some big issues in the design of this kind of class C oscillators. So, to repeat, we have to avoid the differential pair enters the linear region. So, what we need is to lower its DC bias so that we can still have a decently high oscillation amplitude and without entering the linear region. Feedback with the transformers, so not just with the RC high pass filter, but also with the transformer is possible, and we have done that. Ideally, if you do it this way, ideally there is no 1 over F noise up conversion into phase noise. What do I mean with ideally? Well, if the transistors follow the ideal quadratic voltage to current transfer function or characteristic, well, then this is true. Nevertheless, if you compare this with the ideal class B oscillator, but this is a big, it's a big if. So if you compare it with the ideal class B oscillator, then the ideal class B oscillator is still more power efficient than this one. But if you have a real class B oscillator, then the comparison is much less straightforward. It's definitely very attractive for bipolar oscillators, because there you definitely do not want the bipolar transistors to go in so-called saturation. And by the way, if I work you all tomorrow at 20 past 11, come numerous to this presentation, where my colleagues from the University of Padua will present this 20 gigahertz VCO, which actually makes use of this technique. So there is in this case there's a feedback. You see that we have the feedback through a transformer, and then we have a low frequency feedback to stabilize the DC voltage of the gates of the differential pair. You see that in this case the differential pair of PMOS, because it has a lower 1 over F noise, and this filter here is just to diminish the impact of the phase noise of the noise from this DC bias feedback circuit from up converted into phase noise. And and we have a switch here which is good to speed up startup. So at startup we don't care much about phase noise. We want the oscillator to start up very quickly. Then when it has achieved steady state, then we can have a very low cutoff frequency here to kill the noise. And by the way, I can just mention an interesting results that we have just achieved for this kind of oscillator. So if you keep everything in class C, as I just mentioned, there is no 1/f noise up conversion if the transistors are ideal, so they follow the ideal quadratic characteristic. If there is a mobility degradation of the charge carrier with the voltage between drain and source, well, then this is not true anymore. But we have been able actually to, for the first time, to actually produce an equation for phase noise caused by 1/f noise up conversion from the differential pair. And you can see here what the different symbols are. The interesting thing here is that, so this is obviously not 1/f, up converted to 1/f noise around the carrier, and this is actually the admittance of the tank at twice the oscillation frequency, at 2 omega 0. Many more details will be given tomorrow at 11:20. 4 slides about this fancy new concept that we have really tried to make work, but with not a lot of success so far. So please, if you think this is something you can try, please go ahead. Series resonance oscillator. So it's a different approach, basically making use of series resonance. Okay. So instead of having the LC tank, which is a parallel resonance, in this case, it is series resonance. So it's voltage driven, and what we have here in this case is that the gain is equal to the quality factor Q of this series tank. So if we have VP here, we have Q times VP here, okay, assuming a sinusoidal excitation. And of course, there is a 90 degrees phase shift, which we have to take care about. And it turns out that this, at least in principle, can be very interesting to, it's not low power. It actually consumes a lot of, like hundreds of milliampere, maybe. But it really delivers a really low phase noise, at least, in simulations. The phase shift, 90 degrees phase shift, can be taken care of by just having a quadrature implementation, where each of the 4 legs is just an inverter driving a series LC tank. Okay. For the time being, we disregard the very important issue of startup, so that we don't have like a latch up to digital values across the feedback. But you can look at, if you're interested in this, you can look at these papers where this is described. Typically, we have a square wave between VDD and ground. And in this case, the MOS devices work almost always as switches. Okay, almost always. So the channel resistance is directly in series with the total tank resistance. And already here you can understand, I mean, why this is not so easy to make work. Okay, because this resistance, if we have a good L and a good C, this resistance is maybe 1 ohm or not much more than that. And really means that these switches must have a resistance, I mean, must present a resistance, a channel resistance when they are on, which must be much smaller, say, than 1 ohm, if you do not want them to deteriorate the quality factor of the tank. But the nice thing is that if we look at the phase noise performance of this, you can see here. So again, all the theorems that we have seen so far, they do not really apply, because here the devices, they work as switches, not as transconductors. Okay, but we can just analyze them anyway. And F here, this extra noise factor, is accounting for the fact that the MOS are non-ideal switches, as I said, and also that they do work for a very tiny bit of time as transconductors when they are both on. This is very tiny fraction of the period, but on the other hand, they are really huge transistors, huge devices. So they actually, in principle, can make a lot of noise during this very short time. But if you do the calculations and you find it in the paper that I have quoted here, this F is very small, basically negligible. So the interesting thing here is that this, in principle, this topology is capable of achieving an almost ideal performance in terms of figure of merit. You cannot go beyond that. Basically, this is ideally close to 1, perfect as basically all like in class D amplifiers. So ideally the efficiency is 1, and also ideally there is no noise coming from the active devices. So ideal efficiency in terms of power delivered to the tank, and no extra noise from the active devices. And this is, of course, I want to just remark this. It is actually quite different compared to all the other oscillators that we have seen so far, where we said that independently of of the dimension of the transistors, they contribute a factor of, say, gamma n or gamma p to the total phase noise if the tank contributes a factor of 1. The momentous issues, though, is that once upon a time, so the MOS resistance is really critical. So you really need great switches, and this is the largest difference compared to all the other oscillators that we've so far. You didn't need a great transconductance to make those oscillators work. It's enough with a good, or maybe not even so good transconductors. They still are doing very fine. In this case, you really need an excellent switch, otherwise it will not work. And also other issues like the stray resistance of the ground and power supply distribution is very critical. And also we have large internal voltages in the so basically we start with a very low power supply, which is what we have in CMOS, we like 1 volt, and we can actually develop few times this voltage in the internal nodes. Okay, it does not break down anything between L and C, but now if we are going to drive the next stage, this may of course be a big problem. So this is an additional issue that, if you want, is described in the paper that I have shown in the previous slide. And finally, something about the techniques to implement a very wide frequency tuning range for RF CMOS VCOs. So there are a couple of trends. Definitely, we need. So with the scatter aggregation, there's like all possible standards that we would like to address at the same time. So very often you have more than one oscillator working at the same time on chip, and these oscillators should not talk to each other, should not pull each other. This is what oscillators really tend to do. They want to be pulled, and they want to pull very efficiently. And then also the band proliferations really call for a wide frequency, wide tuning range VCO. Ideally, if we have a tuning range larger than 1 octave, that's ideal, because then we can produce easily all the lower frequencies by simple frequency division by 2. So with respect to the first issue, the pooling, a colleague of mine, Thomas Mattsson at Ericsson, came up with this kind of inductor. So it's in the shape of an 8. Okay, you can see it here inside one of the last radios developed by Ericsson for mobile telephones. Because of this symmetry, twisted symmetry, it's very insensitive to external magnetic fields, so external common mode magnetic fields, and also itself generates a vanishing magnetic field far away from itself. So it's really, this really may save the day eventually in a complex chip. It is true that the Q of this inductor is somewhat lower than for a standard inductor, but this penalty is very much acceptable, and that's why this technique is often used. In terms of tuning range, what options instead? What do we have? Well, the most brute force and also the most used, I believe, in commercial products is actually to have more than one VCO. I mean, it's not very exciting, but that's how it is. Like, for instance, in this case from Qualcomm. You can optimize each of the 2 or more oscillators for power consumption. It takes more area, but this is the kind of trade-off that you have. And to repeat, it's very often done. Otherwise, also very much brute force, what you do is that you have a lot of capacitance. So lots of switchable capacitance in parallel to a relatively small inductance. Okay? So basically, in order to cover a distance between F0 and then if you remove all the capacitances, 2 times F0. Okay? The problem in this case is that there's a lot of power that is wasted at the lowest frequencies. At the lowest frequencies, you have a lot of capacitance in parallel to the inductance, and this really means that you need a lot of power, a lot of current to even start oscillations. And once you have started these oscillations, you probably end up with a phase noise which is way below what you actually need. Okay? But you cannot really save power, because if you just diminish the current and to allow the phase noise to get up a bit, the oscillation dies. Otherwise, why not switching the inductance? I mean, on the other hand, I mean, from the mathematical point of view, capacitance and inductance are really on the same footing. Okay? So people have done that. I mean, they've tried to switch the inductance, okay? And they've shown actually that ultra-wide tuning range are possible. But it turns out, at least so far, it turns out that to really have a low phase noise at a good form, a good figure of merit, is difficult. Okay? It is difficult. Additional issue is that if you want to make the inductors in the shape of an 8, for the reason that we've just explained in the previous slides, well, then it's not as easy. It's possible to do that, but it's not really easy to make a switchable inductor in that case. Probably a better idea is to use the transformer VC. We've already seen that people have used transformers to introduce a second resonance at 2 omega 0, for instance, or even 2 more resonances. You can also do that to extend your tuning range. So basically, having a transformer really means that you have two resonant peaks. And then if your tuning range, say with switchable capacitances, across each peak, if they overlap each other, well, then you have managed to cover a much, much larger tuning range. And this has been done, definitely. Also, in this case, very good results. Very good results with a very large tuning range. Also, in this case, it's if you want to go for insensitivity to external magnetic fields impinging on the transformer, well, then you might have some problems in the design of the transformer itself. On the other hand, this has been done here. This is a very interesting work. So it's about in the same spirit, okay? But it's not really. It's a so-called mode switching VCO. So basically, you have like 4 lobes for inductors, and sometimes you use all of them in the high band mode, basically in parallel, and then you have only 2 of them, and 2 of them are basically silent for the low band mode. And also in this case, it's really good phase noise, really good figure of merit. And the nice thing in this case is that this topology does reject external common mode magnetic fields. So it's really interesting. The downside is the downside is definitely the very large area. It has a very large area, and you can see that to save some area, the designers have actually put lots of circuitry inside the lobes. Now, typically, it's not really good to have metal layers and so on inside an inductor, because that tends to really sacrifice its quality factor. But nevertheless, these are measurement results, and I really like this design. Our own take was to have 2 inductors in the shape of an 8, and inside, so you see here, and the small one for the high band inside the big one, and rotated compared to each other by 90 degrees. So ideally, they do not interfere with each other. Ideally. Non-ideally, they do. Especially the problem is that because of all the metal underpass and overpass and so on, the Q takes a hit between 20 and 30%, which is actually a sizable hit. But eventually, if you go and check that our performance covering 1 octave and the phase noise that we achieve, and for the power consumption we achieve, is actually is a rather competitive implementation, I would say. Finally, we can talk about the active cores, and here I skip a little bit because Professor Leeson will talk about this at length. So the idea is to be able to switch between this case, this topology, and this topology, dependently on whether we want to save power. Then we use the double switch pair. Remember that the double switch pair is very nice in the sense that for a given current, it delivers twice as high oscillation amplitude compared to this topology. Okay, so for power saving, double switch pair. If we want to go for the best possible, the lowest possible phase noise, go for this one. And this is our take for this implementation. Especially extremely good, my then postdoc Luca Fanori, who devised a way of be able to switch between the 2 topologies with losing less than 1 dB because of the switching. And you see also that in this case we are helped by the noise filter at the common source here. Very, very powerful technique. And also in this case, we achieve actually pretty good results. In this case, obviously, we were helped by the technology used. So it's a 28 nanometer fully depleted SOI technology, where the parasitics of the parasitic diodes of the switches were less than half compared to a bulk technology. So obviously it was very good. So basically, we were able to switch on and off lots of capacitance without taking a hit in terms of the tuning range. So this brings me to the conclusions. Just a few, it's the jitter, right? So a few jitter of a few minutes on the positive side. And so we have seen the rigorous phase noise equations results, mostly for transconductor-based oscillators. The Class B VCO is really a star of the CMOS IC design. It's simple, it's robust, you find it everywhere. The tail filter improves the phase noise even by a large amount, and in the recent proposals we have a more complex tank that is able to common mode oscillate at 2 omega 0 instead of having explicit inductance. The Class C is more power efficient than the Class B, but also more complicated. Definitely it has the promise of having a lower 1/f noise up conversion. The problem is that the Class C must be enforced in all working conditions. Definitely very good for bipolar implementations, because there you don't have any other option really. And the series resonance oscillator, where I've shown you a couple of slides. The potential is there. The question if it is going to be implementable or not. For the wide tuning, extremely wide tuning range techniques, we have seen several, and as far as I know, there are no clear winners so far. And that's it. Thank you. Yeah, and then there's 4 slides of references.